Hey seniors, welcome to day one of review for our benchmark, which is next week. I'm super excited that we have this time, and I know that a lot of you guys, this is going to be easy review, but my expectation is that you are still taking notes. So let's go ahead and jump right in. Today we're going to cover rational numbers, irrational numbers, square roots, and volume. So let's go ahead and jump in. On your notes page, go ahead and draw your line and then write rational and irrational numbers at the top. All right, you'll recall that rational numbers are any number that terminate, repeat, or that can be written as a fraction. You don't need to write that down. You should already know that. So if I had 3, 4, 5, I know that 3 and 45/100ths is a rational number because 5 terminates in the hundredths place. Let's do another one. If I had, if I had 4/5, this is a rational number because 4/5 is a fraction, and any rational number can be represented as a fraction. Even if I had 0.44444 forever and ever, I know that this number is a rational number because the 4's repeat. They might go on forever, but they repeat. Let's move on to irrational numbers. Irrational numbers are any number that does not terminate, repeat, or that can be written as a fraction. So irrational numbers cannot be fractions, and some of them will not terminate and they will not repeat. So if I had 3, 4, 1, 5, 6, 7, 8, 9, ... This number never stops and it doesn't repeat, so it's definitely irrational. And this should make you recall that this number actually is the pi symbol. And we know that whenever we see pi, we always know that it's irrational. Whoops. Pen's acting up on me right now. All right, so anytime I see pi in any capacity, I always know it's irrational. So if I had 16 pi, I know that it's irrational because of the pi symbol. Another one I could do if I just had 3 pi. The other reason that this is irrational is that it cannot be written as a quotient of integers, okay? Quotient of integers. Quotient should make you think of division, so a quotient is the answer to a division problem. But a quotient of integers is a fancy way for saying fraction. And I know that 3 pi, because it's irrational, cannot be written as a fraction. So it can't be written as a quotient of integers. That's super important. I want to make sure that you guys have that term for your benchmark, because you will see that. All right, let's move on to square roots. If I want to estimate the square root of 10, my first thought that I think to myself is 10 a perfect square? I know that 10 is not a perfect square because I have all my perfect squares memorized. So I have to estimate that number since I don't know what it is. So my first step is to figure out what perfect squares are around the square root of 10. And I know that 9 is a perfect square and that 16 is a perfect square. So I know that the square root of 10 is going to fall between 3 and 4, somewhere in there. My next step is to figure out, is the square root of 10 going to be closer to 3 or closer to 4? And this is where I look back to my radicals. And I know that 10 is closer to 9 than 16. So the square root of 10 is going to be closer to 3. And this is where we start coming up with some of our answer choices. So if it's closer to 3, which is the smaller integer, I know my answer choices are 3.1, 3.2, 3.3, and 3.4. If the square root of 10 had been closer to the larger integer, of course you recall that our decimals would end with 0.6, 0.7, 0.8, and 0.9. But it's closer to the smaller one, so we're at 0.1, 0.2, 0.3, and 0.4. I'm going to go ahead and just pick one and square it, because of course I know that's how I determine what my answer is. So I'm going to go ahead and pick 3.2. And of course our last step is just to square it and see how close it is to 10. So let's go ahead and do that. 3.2 times 3.2. All right, and I remember from math intervention, of course, that I ignore my decimals until the end. So 2 times 2 is 4, 2 times 3 is 6, 0 placeholder. 3 times 2 is 6. 3 times 3 is 9. So the number I'm coming out with once I add is 10 and 24 hundredths. That is pretty darn close to 10. So I can go ahead and say that 3.2 is a good estimate for the square root of 10. Let's go ahead and plot this on a number line, because after all, that's what all of this is about, is figuring out where these numbers fall on a number line. All right, if I took 3.2, I would just look at my number line between 3 and 4. And I know that 3.2 is pretty close to 3, so I'm going to put a dot closer to 3 and just write the square root of 10 above it. And that's it. Now, on your benchmark, you're also going to have to explain your answers sometimes. So I'm going to go ahead and give you an exemplar of a good answer to how I estimated the square root of 10. So I'm just going to go ahead and read it to you. You definitely do not need to write this down. Do not write it down. My first step was to determine which two integers that the square root of 10 fell between. The closest perfect squares were 9 and 14, so I knew that the square root of 10 would fall between those numbers. Since 10 is closer to 9, I knew that the square root of 10 would fall closer to 9. So I tried 3.1 first to see if that was close. And then after squaring 3.2, I realized that that was actually closer and that the answer was 10 and 24 hundredths, which was a good estimate for the square root of 10. That is a pretty good answer. It takes me through all of the necessary steps for estimating the square root of 10. All right, my last thing I'm going to talk about today is volume and cube roots. Of course, we recall square roots, which is just a number multiplied by itself to give you the number inside the radical. So I know the square root of 9 is 3, because 3 times 3 equals 9. But if I have cube roots, I have to find a number that's multiplied by itself 3 times. So if I have the cube root of 8, I would think to myself, what number multiplied by itself 3 times will give me 8? And I know that the cube root of 8 is 2, because 2 times 2 times 2 equals 8. All right, and cube roots are especially helpful when finding volume. And of course, I recall that volume is length times width times height. Definitely write that down on your notes page. So let's go ahead and do an example using volume. A cube has a volume of 27 cubic inches. What is the length of one side of the cube? Well, I already know that I have the volume. So the volume is 27 inches cubed. So I just need to find the length of one side. So I'm thinking to myself, I know that 27 is a perfect cube. So in order to find one length of a side, I just need to find the cube root of 27. So what number multiplied by itself 3 times will give me 27? I know that 9 is too high, because 9 times 9 in itself is 81. The square root of 27, that's not even applicable here. I'm left with 2 and 3. Well, I know that 27 is a perfect cube, and I know that 3 times 3 times 3 equals 27, which means that the length of one side of the cube must be 3 inches. And I can check myself by putting it into our formula. If I do 3 times 3 times 3, let's see what it gives us. Well, 3 times 3 is 9, and then 9 times 3 equals 27. So B is our correct answer. All right, guys. Thanks for listening for our first day of review. We're going to move into practice.